And so you're ready in
Wait a minute, there's
1 minute.
microphones.
Huh?
Microphones?
Oh, I don't know how to use them. You just have to. I never had an issue. I mean, I would talk here and they can still hear me, even if I go a little bit over there. Unless you talk a little louder. Yeah, I don't know how to use this. I never used them. So do you?
Everybody thinks about the same thing you had before, but how the interface.
Yeah, and what is that? Oh. Yeah, this has been like updated, but they didn't give us instructions on how to use it. We're good to go. Oh, it is lower than usual.
It just went down. I touched it.
You touched it? Did it go down when you touched it?
Yes.
What did you do?
It's okay.
I don't know what you did. Is there like a touch button?
But I was kind of surprised.
Is that move it up?
Okay, I'll put my.
Is that good enough?
Sure, you can break up with that.
No. Okay.
Okay. I won't touch it. Well, anyway, I'm Gary Rhinexus. You've probably seen me wandering around, or we've seen each other wandering around one way or another. My area of research is flavor, and from an analytical standpoint, from a chemistry standpoint. And really, there's no better technique for instrumentally looking at flavors than gas chromatography. So basically, I think I've been working with gas chromatography for, well, I won't even say how many years. It's been a long time. So, but that's what I get to talk about today. Then next week, it'll be mass spectrometry, a secondary tool. So these are the two things that I use on an everyday basis. In terms of what we're going to talk about, the name, you may hear it, GLC, gas liquid chromatography. That was what kind of it started off as a naming, but there was really never any liquid involved in it. So somewhere, along the line, they said, well, let's just call it GC. Well, then we had high resolution GC, HRGC. We've kind of given all of those up for just GC these days. That's kind of adequate, gas chromatography. We'll be going through these topics, hardware. So what is the instrumentation? What kind of equipment are you working with? Do you deal with some chromatography, kind of theories of chromatography? Talk about the mobile phase, stationary phase. We'll spend some time doing it. How do we do it the best? And that's really important. One of the things that oftentimes is troubling is that a person will put into a laboratory and you'll be given a tool or say to work a tool and kind of be given, well, this is how you do it. But I really think it's best also you sit down with a manual, you sit down and get some training for it. Because these are instruments. They do exactly what you tell them. If that isn't what needs to be done, you get a wrong answer. And so the idea of knowing exactly what you're doing, what the machine's doing, puts you in a position to get a lot better data, a lot more valid data. Well, we'll deal also with problems and then some applications. So these are the topics we're going to spend time on. Okay. Now, I would have thought a down arrow key would make it go down. Where'd the boss go? She deserted us? Try the space button. Page down, page up, delete, everything? No, shouldn't do that.
Yeah, sometimes you get stuck. I would just go. Try to go here and click.
Oh, sure. Which one? That one?
Yeah. So and then you can go back.
Okay. Always goes that way. So I said I've been working with gas chromatography quite a while. Well, probably not that far back. So chromatography started, somewhere around 1850 when the first chromatography was done. That wasn't gas chromatography. That was looking at separation of colorants or dyes, actually. 1906 is also a date that some people put in, separation of plant pigments by a researcher named Speck. But when we start talking about gas chromatography, that was 1941 was the first publication of theoretical use of this. Your mobile phase is a gas. You think of mobile phase oftentimes as being a liquid, or obviously liquid chromatography, column chromatography. But they said, well, we can do this with a gas as a mobile phase, and that permits us to look at very volatile compounds. 1952, the first gas chromatograph was actually constructed. It was really a clumsy device. They didn't have a good detector, so they'd sit and trap whatever gas came off the end of that column, trap it and try to measure it someplace. How's that? Not very good. 1954, the first detector came into being that actually sat at the end of the instrument, and as things came off the column, it would actually measure something. So we say 1954 is really kind of the birth of gas chromatography. Now, it's I guess, fortunate in the sense that probably 20 years ago, it became a mature technique, meaning we're not going to see any improvements in this technique. You may get more bells, more whistles, fancier things, but you're not going to get better chromatography. You're not going to get better sensitivity out of it. It's really reached the theoretical maximum. So you can go through theory. This is a perfect ideal system. We're as close to that as we can get. So it's a mature technique. We're not going to see any great advances in the future. We look at what kind of analyses are done by GC. You can kind of read that list. And it's a lot of different things, a lot of different things that relate to foods, obviously. And it's interesting that it isn't always best to use gas chromatography, some of those. You might use a better technique, but it is possible. I could do amino acid analysis by gas chromatography. I'd say, why should I? It's easier by liquid chromatography. Amino acids aren't volatile, so why the heck am I trying to make them volatile so I can separate them by a different technique? So, kind of keep that in mind too. If you see people using a gas chromatograph for something, question, was that the best choice? Because like I say, it isn't. So it does, but it does have its place. We look at the process. The sample is volatilized if it's not already a vapor. I could take a sample of air in this room, draw it into a syringe, put it into my system and do an analysis. It's already in the gas phase. I don't have to make that sample volatile. But if it's not volatile, if it's something you've extracted, or it's in a product that can actually just put into the GC, then you have to make that volatile. You've got to vaporize that sample. So if your sample isn't a vapor, let's get it into the gas phase, because that's our mobile phase, going to move with the gas. Passes through a column. So again, like column chromatography, there's a column. Have you done the lab yet in gas chromatography? Half of them have? Okay. Then you're going to be familiar with some of these things, which is good. You're doing fatty acid analysis, and they are volatile enough to run by gas chromatography. When I say volatile, I'm saying something that is a boiling point, maybe 200, 250 degrees centigrade. So, that's a pretty good heat. So your analyte then will move into the gas phase and follow that gas along as it goes through this column. It goes through the column and comes out at the end eventually. And that column used to be glass, it used to be metal, and now it's a fused silica, an ultra pure, ultra strong form of glass. And so the glass doesn't do much but it's inert, and we put a coating on the inside of that glass. So our mobile phase is the gas we use to go through that column, and the stationary phase is the coating that we put on the inside of that glass column. Separation occurs, hopefully, theoretically, and then we have a detector at the end of it. And like I say, I'll go through each of these parts as we go along. So this is a simple diagram of the hardware. We need a mobile phase. We call it mobile phase, the carrier gas. That's carrying our sample. That's carrying what we volatilize. We can't just hook a gas cylinder up to it. We need some kind of a regulator to control the gas pressure, the gas flow regulator as well. And it goes along here. We can introduce our sample here. That's typically with a very fine syringe. This is a very hot port right here, and run 200, 300 degrees centigrade. So you make your injections, go poof, and then your sample is carried through the column. It's in an oven because we take advantage of volatility in our separation. It's one thing that gives us more separating power in gas chromatography. We don't only use an affinity for the mobile phase. We look at affinity for the mobile phase as one unit of separation. The other thing is volatility. Something that's very volatile is going to go with that gas. If it's not very volatile, it's not going to want to be in that gas. So we use both volatility and the affinity for your stationary phase for separation. We got several different kinds of detectors that we use, and they all do draw a line on an electronic monitor. So, okay, we got those. This makes it look a little more like it truly is. We don't have typically one gas. We have one gas for the mobile phase. And our most common detector actually burns what's coming out of that column and measures the ions that are formed in that flame, in that burning. And so we have to have something to burn. That's hydrogen. And we need air for combustion. So we've got two extra cylinders here. And that's to get that detector at the end, have a flame where we burn, everything comes out of it. So you see it's a little more complete with the regulators, the flow controllers. Our injection port is kind of put in where it should be over here. So your gas flow is coming in here, goes through the injection port, here's your injection. Here's your column, comes out, and here's a flame burning. And then, of course, the electronics that detects the ions across that flame. So what mobile phases do we typically use? We typically work with either helium or hydrogen. A little bit later on, I'll mention to you that probably nitrogen is the most effective gas. But there's reasons we don't want to use nitrogen. It costs us in terms of efficiency. And so, like I say, I'll spend time with that later on. So normally we're going to be using helium or hydrogen. Detector gases, some of our detectors don't need any gas. A thermal conductivity that I'll talk about, a thermal conductivity detector doesn't need a gas. So we could get by with just one tank and one gas for it. But again, if our detector, many different kinds of detectors, some of them require ancillary gases to make them operate. So we'll show them too, or give you an idea of what they are. The flow regulators, you will find every tank that we have in the lab has a regulator on it. And they basically do, as I said, they are pressure regulators, first of all, and then a flow regulator after that to control our mobile phase, how fast it's moving through the column. These are sensitive precision instruments. We don't go to the welding shop and get a nice regulator that you use in welding for a couple of reasons. First, it's not really sensitive enough to control the pressure. And secondarily, it's contaminated about all kinds of different things. We need a special regulator that is really clean. It's stainless steel. And so it doesn't put a contamination into the system. The regulators also, you can stop the flow of any of these gases very simply. And then that's where you stop it. You don't crank them down and you don't put pressure on it. So again, when you work with gas chromatography, Be gentle with it. How's that as a way to put it? It is a real sensitive instrument, not it's characteristic of a welding shop. So anyway, and people have to be pointed out because they may have familiar with other gas systems. Whoops, went the wrong direction. So let's take a look at the different parts of this instrument, then a little more detail, so you kind of know what's going on. I said we need a way to introduce the sample, and we need to vaporize that sample. That's what happens in our injection port. That's the place where we introduce. Remember, that gas is under pressure. The gas is flowing in columns under pressure. I'm going to have to put my sample into a pressurized system. How do we do that? And so that's typically done by up here. Here's our gas coming in. That goes up here into a column. And there's a rubber septa up here. Not a rubber, it's a really high purity material. And we can just put our needle in here, pierce the septum, and inject our sample. And we probably inject it someplace up here. This is hot, 200 degrees, 300 degrees, goes poof, and then goes partially into our column. So the injection port, and there's several different kinds of injection ports. We'll go through a couple of them. Maybe we'll go through 3 or 4. But just the idea, you'll have different ways to inject your sample, to introduce your sample into this gas flow. These are 1, 2, 3, 4, 5. Okay, 6. 5. 1, 2, 3. I'll be okay. So our injection ports. One of them, and most common one, is what we call a split injection port. And I'll show you how that works in a moment. But you're going to be injecting 1, maybe 2 microliters of sample. That's a bucket. That's a lot of material. And that simply doesn't work for some of our applications. I need to dump most of that out the machine and only sample a small amount of it to go into my analytical system. So most commonly, we work with a split injection port. Like I say, it gets rid of most of our sample. It gets our sample down to where the column can manage that. Split less, there is no split. What you put in goes on that column. On column, I said that injection port runs around 200 to 300 degrees centigrade. Well, on column, you've got a syringe that has a needle about that long. And so you kind of put that in and you keep on going down past the injection port, down into the column, and you actually inject on the column. And that's because some materials are very heat sensitive. If I dump them in 200, 300 degrees centigrade, they may degrade. And so I want a very, very gentle warming of the sample. And that comes about by on column, the cold injection. There are some 2 different ways to do it. You can have programmed injection ports, maybe your injection port's 50 centigrade, and you warm it up to 250 degrees centigrade in 3 seconds. So put it in where it's cool and warm quickly. In some cases, sensitivity is a real issue. You can inject up to 1 milliliter. Now, if up above 1 microliter is a bucket, 1 milliliter is really a bucket. And so again, you have to have some way to get rid of that solvent. So your large volume injectors are designed to vaporize most of the sample and collect a portion of it, actually go in the instrument. So this is one of those. This is our split injection. This is the workhorse. By far, most gas chromatography is done with this particular injection. I'll kind of go through the flow of it. I know I'm going to lose the microphone over there. So let's say here's our gas coming in. We've got our gas cylinders here, our regulator here. And I want about 54 milliliters per minute of gas coming into my system. There is 2 different pathways, and there are 2 different pathways for that gas to go. One just goes right across here and out to the vent. The other pathway is to come down here into an injection port. And at this point, a small amount goes into the column and the rest goes out this vent. That may seem a little weird. Okay, why are we doing this? Well, this first one up here, 3 mils per minute coming across here, that is a polymer. It's a polymer seal that my needle is going to go through. That polymer, 200 degrees centigrade, is going to be giving out gases, it's going to be giving out contaminants. I don't want any of those gases to come into the system. So whatever vaporizes up here from that septum go that direction, so they get swept right out. Only those things that go down here actually make it into the polymer. So 3 mils go there, 51 mils per minute comes here. Of that 51 mils per minute, 50 of it come out around this and go out that vent. 1 goes into this. So that's a 1 to 50 split. You're only taking 1/50 of what you injected in your column. There's different pressure gauges and so on, but please, let's worry only kind of about the flow of the gas systems. It's worthwhile to pay attention to flows and what's happening. It's probably 80% of your problem is the gas flow. Gas flow didn't go where you wanted it to. So it's kind of nice to know where it should go. And this is where it should go. Sure.
Rates stay the same, the 50 milliliters per meter and 3 milliliters per minute. Do those stay the same in the split injection, or does that vary?
That's a nice number. We'll just give it credit for that, huh? If you've got a sample that's maybe a little weak, maybe instead of having 50 mils per minute come out here and go that way, maybe have 20 mils per minute and 1 mil going here. So you get 1/20 of your sample goes in the column. So you can change the amount that really gets analyzed by changing that split ratio. You could use 100 mils, so it'd be 100th of your sample, 1/50th, 1/20th, and so on. You get kind of in trouble if you go too low. 1 to 10, yeah, that's tough from an efficiency standpoint in splitting. But that's how one way you control your sample that gets into your instrument. Here's our on-column injection. And as I said, we've got a needle. It's a very long needle. And there is a valve here. So this is your injection port. And so you actually get your needle, come down here, come down here. Now this is your column. This actually goes into the analytical column, dumps your sample down here. It's really gentle. Some things do decompose. So thermally decompose. And this is a good way to kind of ensure that it's as gentle as you can get. I did want to stop and pick up a column, and maybe I'll remember next time, of the good old days, as people like to call them. I call them the dark ages, when we used to use rather large columns. That's a 1/4 inch column. It's a little smaller than your finger, but not a heck of a lot smaller than your finger for diameter. Or we're looking at capillary columns, which I hope you did get a chance to look inside the instrument. Here we're talking about millimeters of depth. And so that glass is a fused silica glass. It's ultra high purity, ultra strength. Again, I don't know what you saw in the laboratory, but you can take my glass and you can tie the knot. And it's that strong and that flexible. And so here we've got this glass that maybe 30 different columns wound around this cage that goes inside of the oven that you see. And inside of that glass, we put a very thin coating. So we, the people you pay to buy your column from, they put the column coating inside, and that's actually chemically bonded onto the glass. So that chemical coating inside of that column, we really want to stay there. I don't want to measure the degradation of the column or the column parts leaking out. And so they put a lot of effort into making this a very stable and a very pure system. So generally it's called fused silica. The inner diameter ranges from 0.1 to 0.53 millimeters. Today, 0.53 is immense. We deal much more commonly with the, let's say, 0.2 millimeters. Length, 1 to 60 meters. Can you imagine 60 meters? That's a good long column. Do that in liquid chromatography, or do it in column chromatography in your lab, 60 meters high. Okay. So we've got the ability to use long columns for tougher separations. And that coating inside, we can choose that coating. We can choose the thickness of that coating. The thinner the coating, the more efficient the column. But the thinner the coating, the less it handles your sample well, quantities of your sample. So there's always this compromise. And so very commonly, we use about a 0.2 millimeter, I'm sorry, 0.2 micron coating on the inside of that column. So that's something about the column. These are the stationary phases, the coating that's put inside of that glass tubing. There's 1, 2, 3, 4, 5, 6, 7, 8 or 9, maybe 9 coatings. We used to have 300 coatings, again, back in the dark ages, simply because we didn't have the efficiency. We didn't have good systems. We had to pick a coating that really, really did the job for us because everything else wasn't very good, efficient. And so we use 300 coatings. Today, we're down to 9. It's so darn efficient. The column doesn't have to work so hard for us. And so if you go in the laboratory, you'll probably only find 3 of these in the laboratory. And so there's really been some nice advances in columns and efficiency of columns. There's a question always is, well, I've got a separation. I know that I've got a mixture here. I have to separate it. Which of those coatings do I take? What do I try? And so the first place to start looking is the published literature. There are what I say Kovacs indices. That's Kovacs is the fellow who developed this whole system, or retention indices. And that the retention indices, it tells you on a certain column, certain coating inside the column, this compound is going to come out at a certain time relative to other compounds, reference compounds. So it's like a published book. It's a reference. And if you want to know if you can separate this material, if it's a good material to use for your separation, you can go to literature and you can say, oh, look, this is what they used in the literature. And okay, that's what I'm going to use or not. So the literature is really good. It's gotten so much better in the last few years. And of course, you go to journal articles, you look up what did somebody else do in the past. You're probably not the first person in the world to ever done this particular separation. So you go look what they did. Don't ever assume that's correct, but it's a good starting point. And so what did somebody else do? If it worked for them, should work for you. Is it the best? That's another question. And of course, internal work. If you work in a company, hopefully they've done a good job of documenting what they're doing and how they're doing it. And someplace in the archives, you should find a reference to the methodology in this separation. So you can find oftentimes information to give you an idea of what coating to use for the separation you want. If you can't find anything, then you go for intuition. There's an old saying about like attracts like, I think. And so the idea, you want a coating inside the column that likes certain materials, that'll interact, that'll hold them up, that'll separate them. And so the idea that these coatings are different materials. If you know what you're looking for, you know its chemical properties, you can find a coating that's similar to the chemical properties of what you want to separate. And so there's kind of the whole idea, let's do the literature, let's look for what's published, what's been in-house. Oh, nothing. Okay, well, I think this is a good choice, so let's try this. And if you can't find anything, and that's going to be tough today to not find anything. Somewhere you'll find something, but if you can't find anything, then you always start off with a non-polar column, and that's I'll show a little bit later on. A column that has coating is very non-polar. And that's simply because they're extremely durable. I can take that column and I can warm it up to 400 degrees centigrade, and it's going to sit there and be happy. And so I can work at high temperatures. That helps me get things through the column so that maybe I see them. So if you don't have any idea, I take a very durable column, I inject it, and I see what happens. Some of the columns that we do use are polar, and they're not very durable. And if you would do that, heat up to 400 degrees centigrade, you'd be at about $600 to get a new column. How's that? So I start with something very strong, very durable. And if that doesn't work, I go more gentle, but use a polar phase. You take advantages of all of the techniques in chromatography, common type techniques. You take of absorption chromatography, molecular exclusion chromatography, partition chromatography, and vapor pressure. So each of these basic principles of chromatography, separation principles, you can take advantage of in gas chromatography. And as I said, we add a fourth one that you typically don't take advantage of by LC or by columns, other techniques. And that's vapor pressure volatility. So the idea that we can combine separation techniques gives us, again, more separating power, more efficiency than many other techniques. We look at our column coatings. As I said, they range from very polar to non-polar. There's a trade name that identifies our polar columns, and that's Carbolize. So that is a coating inside the columns, very polar. I want to separate polar compounds. That's my material. For non-polar, then they are silicone-based. And it's a little frustrating that companies may give their own names. And so you may want a non-polar column that may have this name from Agilent, it may have this name from another company or this name from another company. And that's a little confusing. That certainly could be improved. How's that? So that's our columns. Column ovens. Well, like I say, these are put in an oven. And that oven actually can go anywhere from -60 centigrade. You're going to have some outside cooling, of course, for that. So from -60 to about 400 degrees centigrade. So you've got quite a range in volatility, boiling point you can manage. Nobody goes so cold. One of the compounds I'm interested in is hydrogen sulfide. The smell of hard-boiled eggs, a sulfury note, that has a boiling point down in that range. I want to separate from something closely related to it. To keep it in that column and keep it moving, I have to get down to close to the boiling point of it. So for real difficult separations of very, very volatile materials, you may have to do that. Not routinely. Most of the time, we start off around 40 centigrade. That's most common for us. But there are times when we've gone lower. So, okay, we've got our gases, we've got our column, we put our column in an oven, we then take that column, we stick it into a detector. So what do we have for detectors? Well, what's our goal? Our goal, obviously, is to turn the presence of an analyte that's coming out here into an electrical signal that can be integrated and managed by your data software handling system. And so there's an example here is what a chromatogram would look like. There's a large peak initially, that's a solvent. So whatever this sample was, that was a solvent with it. And that's the first thing that, typically the first thing that comes out. If you pick a very volatile solvent, you would want a non-volatile solvent that would come out maybe someplace in here, confuses my run. So a very volatile solvent. Okay, here's my first compound, my second compound, and so on. And if you run that chromatograph in, by all good techniques, that compound at 1.769 minutes is going to come out at 1.769 minutes every day, every time you go in there. It might be off by 0.002 of a minute, but it's really accurate. And so very reproducible. So what are we doing? We're turning concentration, comes out of a column, into an electrical signal that we manage. We have many types of detectors. They vary in sensitivity, they vary in selectivity. So those are two issues. Are they sensitive to the concentrations we have? Are they selective in any way for the materials coming out? And we sometimes want a detector that's not selective. I want to measure anything and everything. In other cases, I'm really interested only in pesticides. And maybe even chlorinated compounds. So I pick a detector that ignores everything and only gives a peak when it's a chlorinated compound. So we take advantage of detectors for both sensitivity and selectivity. I'll go through our most common detectors. And again, there's a number of them. This is the first detector that was designed for gas chromatography. I think that was 1954. They came out with this particular detector. It's not very sophisticated, but it's called thermal conductivity. And what we have is we've got two parts to the detector. Here we take the gas that's coming out of a reference cell, and that comes through here. The gas is here. And this is a filament, a heated filament. And so if we've got gas flowing across here, this is heated filament, we keep track of the temperature of this filament. There's a certain amount of cooling that happens from the gas coming by. If that gas changes in composition in any way, it changes the cooling. And so it changes electrical flow. So basically, this detector, and that's shows now, I've got an analyte in here, the blue triangles. And so, and anything that comes through there that changes the cooling, and that's anything, will end up giving us a signal. It's called a universal detector because it detects everything. I can detect water, I can detect helium, I can detect amino acids, I can detect sugars, whatever. And that makes it really sound like a wonderful detector, which it is, but there's a problem. So here's my universal detection. Sensitive to 10 to my 7th grams per second. So that's the flow of the carrier gas coming out. That's listed as grams per second elution time. Now, 10 to my 7th grams may not sound like too much material. Some of these sounds fairly low, but some of you can carry around in a bucket in comparison to other detectors. So 10 to my 7th gram is poor for our detector. Get this tiny column, tiny injection. We really need quantity, or we need one heck of a good detector, a sensitive detector. So we love this detector for its universal nature. For doing gas packaging, I can pick up a gas package to food, right? And I can take a whole food syringe, and I can detect the gases inside. Did they do a good job? I can detect water, like I say. It's a universal detector. Not very sensitive, not as sensitive as oftentimes we need. And its linear range is only 10 to the 4th. What that means is the compounds eluting from this column and being detected can range in concentration no more than 10 to the 4th. So if there's more than a 10,000-fold difference between this compound and this compound, I won't get a linear response. And linear response is important for quantitation, for estimating quantities. You might say 10,000-fold difference. That seems like a large difference. Well, we can work with a 1,000,000-fold difference in concentration. And I want an accurate relationship of each of these compounds that are coming out. I want a quantitative estimate from them. So basically 10 to my 7 grams per second, 10 to the 4th dynamic range isn't very good. So it's like everything else in life. You get this, but you lose that. So I got a universal detector, but it's not as sensitive as I would perhaps want or need. Depends what you're doing. This is the workhorse. At one time, I would have said probably 90% or better than 90% of all gas chromatography uses this detector. I'm going to probably bump it down to maybe 65% or 70% because of mass spectrometry. Now we put a mass spectrometer as a detector on the end of a gas chromatograph. That's extremely powerful. We'll talk more about that later. But this is, like I say, at least our workhorse for at least 65% of all chromatography done around the world uses this detector. And so here's our detector. We have, here we have our column. Our column is coming in, our analyte's coming out of this. It's coming in our hydrogen or our helium carrier gas. comes up here. At the same time, we're going ahead and putting hydrogen in here and air in the environment. And so we've got hydrogen, we can light a flame. So everything coming out of this column is burning in that flame. Right above that flame, or you notice almost touching it, we have something that's a grounded, well, it's not grounded, but it's measuring the electrical potential between ground and this column. So what we have is we have the ability to measure the ions that are formed. Right around here, we measure the ions, and that gets detected. So anything that burns, we can detect, creates ions, we get a flow of electricity across the flame, and we detect the compound. So that's, like I say, our most useful. I'll go through some of its attributes. Specificity, most organics. What are we interested in foods? A lot of time, organics, right? Organic compounds. So it's the right material. Sensitivity, 10 to the minus 12 to grams per second. If I get that flow, that concentration coming out of my column, I can detect it. 10 to the minus 12 grams. No, that's okay. You don't carry that around a bucket. That's getting a small amount of material. That's for organic compounds. Linear range, 10 to the 6, 10 to the 7. So I can get concentrations differences between two compounds to be more than 1 million in terms of concentration, and I can get an accurate estimate of the relative amount of the two compounds. And so this ends up being one of our most common detectors in the food area. There are some additions to it, some modifications that can make it sensitive to certain molecules, or I should say atoms, I suppose. Nitrogen specific. So I've got a detector that only detects compounds containing nitrogen. And I guess I'll go into some other ones as well. This is an electron capture detector. So this is a rather interesting one. Again, different style, different purpose. Here's our column coming out with our analytes, our carrier gas, coming up here, coming out of the end of the column. It flows through this chamber and goes out the vent on top. Well, this is radioactive. It's a radioactive core. It's basically giving up electrons as it degrades and undergoes decomposition. And so what happens is that we will always have a certain current, electric current. This is giving off electrons. This is measuring the electrons. So we've got this current always flowing. If I put an organic compound through here, it may or may not absorb electrons. If it absorbs electrons, I get a signal. Oh, my electrical flow has changed. So I've got a detector that will detect organic compounds that absorb electrons. That gets us a lot into pesticides and herbicides. And so this was the workhorse for many, many years for pesticide analysis, pesticide herbicide. So a nice detector, seeing much less use again because of mass spectrometry. This is our characteristic of that ECD detector, the PASS detector. It is exceedingly sensitive to halogens. Most organic compounds, yeah, it doesn't do much for them. But put a chlorine in there, for example, a bromine, and we find it's very, very sensitive. No response to most compounds, sensitive to halogens, some carbonyls, nitriles. Sensitive, no, it's 5 times 10 to the minus 14 grams. Okay, I've gone from almost no detection in thermal conductivity, 10 to the minus 6 grams, 10 to the minus 12 or so for the flame ionization. Now I'm at 10 to the minus 14 grams. That's doing okay. Linear range isn't great, so quantitation gets to be a little more challenged. But again, if pesticides are present in low levels, you need that sensitivity. This radioactive detector, or these radioactive detectors, really have the upper temperature limits too. Because you can get that radioactivity from tritium or nickel-63. And you can boil them off into the room. That's not a good choice. So anyway, the sensitivity is just use temperature limits. This may be how we're getting down to maybe the last one or two. And these tend to be very, very much the same. This this one and the next one. And in this case, what happens is you have your effluent from your columns, so your capillary columns going to the materials in here. We can have a reagent gas here that reacts with the organic compounds in there. It gives off light. It's like emitting light. It's, in some cases, this is burn. In some cases, it's a chemical reaction. But it basically gives off light. And here's a photosensitive tube. And it's a filter that only allows light that comes from fluorine, for example, or light that comes from sulfur. And so it's a very specific detector. So this is chemiluminescence, what it's called. It's a chemical reaction to make compounds, certain elements give off light in the process. Flame photometric is very much the same idea, but in that case, our column is coming up here. We have a flame burning, and that flame will take on a color, depends upon the elements present. I'm sure someplace in life you've seen atomic emission or this type of thing. So if you go to the Science Museum, I don't know if they still have it, but they got the flame, and you can then draw in this element or that element into it, watch the flame change in color as it detects different materials. But the same kind of thing. So there's a filter up here, and this works well for sulfur. It's one of our most useful materials. And so you have a filter that only lets through the wavelength of light from sulfur burning. And so again, very specific detector, good sensitivity, and very specific. There are others, the Fourier transformed infrared used to be used a lot. It's used less and less. What is the number? Well, number 2 yet is the mass spectrometry. So putting a mass spectrometer at the end of your gas chromatograph. It's extremely powerful. You know, every compound that elutes from your column, you know, it blows it into bits and pieces, and then the mass spectrometer looks at those pieces and said, I know what that was. And so it's really a beautiful technique for gas chromatography. We'll spend more time with that later, so you're going to get more along these lines. The idea, oh, okay, I guess we're going to go through it now. You know, there's always a problem when you see, you know, you're looking at your gas chromatography, you get this peak here, and it comes along and you say, gee, that's where my compound elutes. That's probably my compound. And, you know, that's probably my compound isn't good enough. And so you really want to be certain sometimes that you are measuring exactly what you think you are. In the flavor business, we've got 11,300 aroma compounds that have been identified. Now, what makes me think that I've been able to separate that one from those 11,300 other ones and be absolutely certain of it? If your life counts on it, or your business, staying in business because you pass inspection or not, whatever, you really want to know what those compounds are oftentimes. And that's why this is such a powerful, and one reason, because it literally blows them up and looks at the fragments and says, yep, those fragments are from a certain compound. And I'm going to give you an example of something that I just am so fascinated by. And that's the idea that you can quantify compounds without separating them. They have 2 compounds and they look like they co-elute. They look like a perfect peak, but they may be made up of 2 parts. You can separate those 2 parts by mass spectrometry. And that's what I think is one of the most important or interesting aspects of it. You'll never be able to see this, obviously, but there's just my chromatogram. I've got all kinds of things coming off my GC. And I'm really interested in what might be there. That could be really interesting to me. So I can actually cut that. I can freeze it out, what's called heart cutting. I can cut it out, and I can re-chromatograph it. And if you would be able to do that, you'd find out and then do the separation. There's one peak here. That one peak is orange, and that's here. It actually comes from this compound added to this compound. So what you're measuring is what looks like a really good peak, symmetrical, whatever. It's actually made up of 2 different compounds. And so it's really neat. What's happened with mass spectrometry is that you can track these ions. So what this does, blows them into pieces, creates ions, you measure those ions. And it measures them very quickly, and it starts saying, okay, there's maybe, 100th of a second difference between the peak here and the peak here. So maybe 100th of a second difference between those two compounds, but all the ions from this are 100th of a second different than the time that is. So by looking at times, you can get this set of peaks, this set of fragments is coherent, and that's from that compound, and this set is doing a different compound. You can do a separation quantitation without separation. I think it's fantastic. And that's one reason why mass spectrometry has become such a common detector, useful detector to us. What time do we quit? What, we got a whole minute? How long? At 40, 140. Okay, so we'll do the next 4 slides. I'm teasing. So anyway, I'm going to give a little more example on this because the power of this is immense. So anyway, we'll pick it up next time. Thank you. Painful. I don't know if I get better or if I get worse. I don't know if I get better or worse at this, but
Better or worse?
I don't know. If you give something too often, do you start screwing it up, or do you just get better at it?
Sometimes this way and sometimes the other way.